So we'll just call this the first half, just formation of the solar system, a theory. So we're done. Unless somebody finds a Oort or Oort Cloud, we have all of the constituents of our solar system, and we tried to do it in such a way that we were like as general as possible. So we talked about, debris disks and gravitational influences among the big bodies that are around them and tug them. Neptune pulls stuff out of the Kuiper belt. Jupiter pulls stuff out of the asteroid belt. And we talked about these things kind of in groups because we're now in a situation where we have 2,500 planets observed around other stars, and maybe they all look like this. Yeah. Yeah, the reason the Oort cloud is included in our solar system, and by some estimates, so there is actually like a boundary that people put on the solar system. And if you've heard this thing, Voyager has left the solar system, it means something very specific about the solar wind. The reason it's in our solar system for these purposes is that Oort cloud objects are gravitationally bound to the sun. And they're not free-floating in space. They've been hanging out around our sun, orbiting slowly, but they're still orbiting over the last 4 billion years. So just because this is all like one big gravitational happy family, sometimes unhappy family. And if there are other things like rogue planets, or if, Nerebu or somebody came by and stripped off part of the Oort cloud, they would no longer be with us. But they care about the sun's gravity, so yeah, absolutely. Yeah, the Oort cloud is centered on and depends on the sun's gravitational influence to keep them bound to us. Yeah. Not necessarily, but it's absolutely true. So, what it means is that the center of the collection of mass, it happens to be. The sun does happen to be very massive, but the stuff that's farther out depends on the gravitational influence of the stuff inside of its orbit. It doesn't care about its density, it just cares about its total mass. So if I'm a little Oort cloud object and there's a tremendous amount of mass inside of my orbit, I'm going to remain orbiting it. So if the mass is puffy or not turns out to be not quite, don't really need to care. Okay. Good. So I do this a little bit backwards than the textbook because they give you the formation of the solar system first, which is kind of weird. It's like reading a murder mystery backwards where you figure out who did what and who killed whom, and you don't care about the characters at all. So now you guys are invested in these objects, right? This is, I don't know, it's the least favorite picture I've ever seen of this. So now we have to explain how this stuff all came about and have a scientific theory. And, we only have really detailed information, or certainly up until, like 10 years ago, about one solar system. And we'll try to do our best because, you don't get a lot of really intimate pictures of solar systems. So maybe this is our one chance of getting it right, this theory of how this stuff came about. And of course, totally not to scale. The relative sizes and the relative distances are freakishly bad. But what do you see? So what are the overall trends in the solar system that we're going to have to explain if we have a successful theory of the formation? It is really flat. Like everything hangs out in the ecliptic. So the Kuiper belt starts getting puffy, but it's still centered on the ecliptic. Maybe it's like 20, 25 degrees puffed out. Asteroid belts, 10. The planets all fall within a couple of degrees of the ecliptic. Yes, so we need to explain that if we're going to do it right. We don't have like random orbits of things in any given direction, like a hive of angry bees. What else? So there's some other motion that's not orbit, but rotation. And all of these things rotate. And in fact, if you were to look top down, like from the North Pole of Earth down, everything aside from 1.5 things are orbiting in the same direction. So looking straight down, everything seems to be orbiting north downwards. Everything seems to be orbiting counterclockwise. The two exceptions are Venus is a weirdo and is orbiting backwards and very slowly, and Uranus has been tilted 90 degrees. Its rotational axis is 90 degrees tilted from the ecliptic, so it's sideways compared to everything else. But those two exceptions aside, everything is rotating in the same direction that it's orbiting. If you remember that asteroid discovery video, all the asteroids are swirling in the same direction. So there seems to be a preferred direction. Sun's actually also rotating. It's got the same preferred direction. So the orbits and the rotations, absolutely. What about compositional trends? Yeah. Yep. So small rocky planets close, gas giants out, and then we also have this second trend where few volatiles. We actually live on Earth, which is water rich. Maybe that was a quirk of just picking up some really fortunate comet impacts. But farther you get out, the more likely you are to see things like ammonia and ice and water. And Europa has one of the moons of Jupiter has so much water on it that it could cover Earth in like 10 kilometers of ocean at least. So farther you get out, the more ices that you see. So we need to explain that. Good. Anything else? What's that? Yeah, they've all been differentiated. And in order to be differentiated, that might take some time. So they all seem to have had enough time to settle. So maybe that's the theory part. So they are absolutely all differentiated. Good. Anything else? Let's go more volatiles further out. Inner planets small and rocky. Outer planets big and gassy. Everything rotates counterclockwise around the sun, looking down from Earth's North Pole. And then I'll throw something else in there that we didn't really talk about explicitly but was kind of important, is that now that you're kind of keyed in to think about impacts, every time you look at the moon, it should like stand there in haunting terror because it's the living history of a lot of impacts. And the Apollo astronauts got there and they started dating some of these craters, and it seems like there was a big pulse of impacts that is centered on about 3.8 or 3.9 billion years ago. So fortunately for us, stated another way, is that the rate of impact has drastically died down over the last 4 billion years. So we do not get hit as hard as we did in the 4 billion years ago or so. Good. And then everything lies in the plane of the ecliptic. Great. So if we're really good, we'll also have a way of explaining the exceptions to the rules. So this is what we need, and this is what we'll get now really quickly. This is something called Nebula Theory, and it's actually this kind of closed cycle of life kind of thing that will close when we talk about star life and star death. So we just got to start somewhere, and so forgive me the sort of really unexplained, kind of gratuitous Deus Ex Machina kind of beginning of this, but we have to start somewhere, and eventually we'll close the loop. So Nebula Theory postulates that in the beginning there was a cold cloud, and the cold cloud was chemically enriched, and the cold cloud was very large. And by cold, I mean 30 degrees above absolute zero. So liquid nitrogen is 77 degrees above absolute zero. Room temperature is 300 degrees above absolute zero. So to put it in Celsius, it would be like minus 250 or so, 240 Celsius. So this is a very, very, very cold cloud, and we'll see why it needs to be cold in a bit. And it's chemically enriched. It's not as chemically enriched compared to, the background of the universe as Earth is, but chemically enriched means it's got more than 2% other stuff. So most of the universe is hydrogen and helium, but 98% of this chemically enriched gas is hydrogen and helium. There should be some helium in there too. It's got about 1.5% of volatiles, 0.5% of rocks, and 0.1% of metals. And it's huge. So this would be about a light year. So this thing is, maybe like a light year or so across. And what happened is something bumped this cloud, this giant, cold, chemically enriched cloud. We have evidence that for us it was actually a nearby supernova, because there was a lot of supernova debris that was evidenced really early in really, really, really old rocks. But so say it's a nearby supernova, this thing goes off and it bumps the cold cloud of gas, and the cold cloud of gas starts collapsing because it's really cold and there's nothing to stop the effect of gravity. So you have something that starts at like a light year and it starts collapsing. It gets smaller and smaller, and something that, if you've had physics called conservation of angular momentum. If you've ever watched, any Olympic games, the figure skating, or played on a couple of pieces of playground equipment, or just screwed around on an office chair and taken your arms and pulled them in, what happens to you? You spin faster, yeah. So you can just call it the figure skater effect. So figure skater's spinning around and he takes his arms, pulls them in, spins faster. This is a dyed-in-the-wool law of physics. So nobody will contest this. It's absolutely, required again by Newton's laws. So now we're doing this on an absurd degree. We have this cold cloud of gas that was 2 light years across, and it starts collapsing into maybe 100 AU or 1,000 AU. So this is not this. This is, tens of thousands of times more. So something else happens as this thing spins and starts spinning faster and faster and faster as it gets smaller and smaller and smaller. It does what pizza dough does when you do the exact same thing. So you take a blob of pizza dough, throw it up and spin it, and eventually it flattens out. That's also conservation of angular momentum, but you could just call it like the pizza dough thing. So spins out into a disk. And all of this is physics 121 or something like that. So sort of something had to bump it to start this off. There needed to be some sort of perturbation to cause and that's actually not obvious at this moment, but it agrees with observational evidence that, remember, I have to start the story somewhere, and when we talk about star birth, you'll see why there's a lot of evidence that it needed to be shocked. But something had to happen, to kind of start this in motion. Yeah. Yep, exactly. Okay, so we have a thing that's called a protoplanetary disk. And in fact, we're doing really, really well, because what have we explained? So we've got this cold cloud of gas out of which planets and stars a star will eventually condense, and it spins out, flattens out, this kind of like pizza dough shape, and it's actually spinning a lot faster than it was before. So we've got 2 facts already, right? So what is this thing which we're now calling protoplanetary disk before the planets? This plane is actually going to be what? The ecliptic, exactly. And this is going to be the direction in which the planets orbit, and then also the direction in which they spin. So we're doing really well, and we haven't had to really work too hard for that. That's just some mechanics and physics. Okay. So as things start condensing, gravity starts taking over, maybe gas drag pulls some stuff in towards the center. You get more molecules and overdensity. If I start pressing molecules together, they collide, they heat up. Eventually, I'm going to have enough mass to form the sun. Before it's called the sun, it's called the protosun. And I'm going to get a temperature gradient. So where I have a lot of density and a lot of stuff bumping into a lot of stuff, I'm going to be hot. And then farther out, I'm going to be colder because I'm less dense. And so now I actually have an explanation for the composition. So if you're really close in and this uniform distribution of metal, rock, and volatiles, the first things that are going to condense and form little particles, solid particles, are going to be the metals, because the gases and the volatiles are not going to condense. They're too hot. As I go farther out, I'm more likely to get particles of rock and metal, and then as I go farther out still, there's this line called the frost line. Eventually I'll get volatiles and gases and rocks and metals. So just the virtue of having, a really hot thing in the center means that there's no way I'm going to get anything but rocks and metals to condense here. Everything else is liquid or gas or pushed away. So now I've got this really elegant and believable sounding theory of why I will eventually get rocky planets in close and icy planets farther out. Does that seem plausible to everybody? You would never expect to see a Jupiter at Mercury's distance, would you? Okay, so now that we have a little bit of compositional separation and we've got a nice disk, everything swirling around in the disk, we start getting, as the temperature cools down, things will bump into each other and condense and make little kind of metal snowflakes and balls of dust and globs of ice and gas. And gravity lets the rich get richer, because if you are a bigger blob of stuff, you have more gravitational pull, you pull more stuff onto you, you actually have more mass, then you have more gravity, then you pull more stuff onto you, which gives you more mass, more gravity, and you get this runaway process where really big clumps of stuff start to form. So this, some little random overdensities eventually run away and become planetesimals, so pre-planets. So they're probably not differentiated. They're just big and massive, and they're cleaning out their orbit. So you get a bunch of little planetesimals that grow, they get bigger and bigger, and then eventually you get some things that are, kind of planet size, Earth mass size. Good. So now we have to deal with a bunch of really random, unstable, overlapping, chaotic orbits. And the thing that we occasionally have to deal with, once every 100 million years or so, some big asteroid or comet will hit us because it got perturbed. This was much more frequent back in the day of this runaway accretion phase and all sorts of random things interacting close by. And in fact, there was much more mass back in the early days of the solar system 4.5 billion years ago than there is now. So you actually get this rampant gravitational slingshot effect. So all sorts of things are coming close to each other. Their gravitational influence is flipping things in every direction, kind of like what happens when you make a comet, but much more frequent. So this is what's called late heavy bombardment. And this is our 4 billion year ago and earlier. We lived in a shooting gallery. So there was more stuff. The universe had not settled down, the solar system had not settled down into established orbits, and gravitational slingshotting was just throwing stuff away. So this is what we'll call just cleaning up. So it's really just this, the exact same gravitational slingshot thing. So that's our explanation for late heavy bombardment, which explains a lot. So it explains the exceptions to the rule. It explains the really heavy early cratering history of the moon. It actually explains why the moon is there in the first place, because it's a weird thing that we have, right? So we didn't capture the moon. It's way too close to the ecliptic, and it's totally compositionally similar to us. It wasn't a captured planetesimal. It's in too nice of an orbit. So the fact that Uranus is tilted 90 degrees on its side, maybe Uranus got blasted by something during late heavy bombardment. Venus is basically spinning backwards and very slowly. Late heavy bombardment did it. Late heavy bombardment is the thing that you blame, it's the ultimate scapegoat in solar system formation theories. If you don't know why something is weird, you just say, oh, late heavy bombardment. Yeah. Why do we have oceans? Late heavy bombardment. Venus. Presumably, yeah. The presumption is that it was hit by something during late heavy bombardment that stopped and changed its rotational period, presumably. Otherwise, it should be spinning kind of comparably to Mars and Earth. The reason Mercury isn't spinning as fast as you might think is because the sun's tidal influences are strong enough to have almost stopped it, or just put it into a 3-to-2 resonance. So apparently the moon is from this period too, and during the end of during the formation of the solar system, not late heavy bombardment proper, a Mars-sized planetesimal came and struck a planet whose name I forget. It's not Earth, because this is how Earth came about. And the debris actually condensed out into these two planets. So I think this is the one with the really terrible soundtrack. So I don't know why, I kind of enjoy it. The worst music is better somehow. So this is one of two kind of reasonable simulations. The nice thing about this is they actually show you the debris disk condensing into the moon and probably how it happened. It's too much. So giant impact, something about the size of Mars, and then this debris disk will eventually start condensing into the moon. So same thing, debris interacts with debris. Eventually you get larger clumps. Larger clumps have more mass, therefore more gravity, therefore they accrete more, and the rich get richer, and let this thing go for a while, and eventually what you'll get is a moon. So this is actually, silly music aside, this is actually like a simulation. This one, if I remember correctly, is much prettier and worth watching, actually. So this is how early it was in the solar system when the thing before Earth got hit. Also somewhat ridiculous soundtrack. So little to no differentiation. This is also fairly accurate in the sense that both of the impactor actually sheared off and left a chunk of what's now basically Earth. And then this is this is a little bit too fast, but the debris condensed back into the moon. And back then, the moon was so close that the day on Earth was, maybe like 10 hours, less than 10 hours. And the moon was much closer, so it was a very sort of hellish moonscape. Would rise above you every like 8 hours or so. So we've had time to cool down and differentiate since then. So that's the intervening like 3.8 billion years. Okay. So finally, the solar wind sun actually turns on, and the proto-sun was actually putting out a lot of radiation too, and clears up all the debris. So you can imagine this is just like kind of feather dusting away all the rest of the crap in it, and voila, we have a solar system. Right? So let's see how we did with this story. So the idea of a frost line, or the temperature of the proto-sun, explains how we got more volatiles farther out. Inner planets are small and rocky. That's also the idea of the condensation temperature, because if you're closer to the eventual sun, you have a higher temperature, and therefore only rocks and metals can condense, not volatiles and gases. Same thing, outer planets are bigger and gassier because they're able to trap more of the gases. Everything rotates down in the same direction, both rotates and orbits. That's the protoplanetary disk idea, just the conservation of angular momentum as the big cloud of gas starts condensing and spinning. This idea of an early terrible time in our impact history. This is late heavy bombardment during the cleaning up phase. Everything but the Oort Cloud lies in the plane of the ecliptic. Protoplanetary Disc got that. And then we also get the exceptions to all of the rules, like Venus and Uranus and our co-planet, the Moon. We can just blame late heavy bombardment for that too, apparently. So this is very, very successful. This theory dates from like 1843 or something like that. So this was actually pretty impressive. This is like cutting-edge thermodynamics and an understanding of gravity, and people totally patted themselves on the back for doing this, I would imagine. This would seem to indicate that our solar system is like pretty generic, right? So if you were to go to another star and look at the planets around that other star, would you expect to see only terrestrial planets really close and gassy planets farther out? Do you expect to see everything lying in the plane of the ecliptic? You'd really kind of expect this to be a generic story, and people thought so. So of the 2,500 planets that we've seen around other stars, especially the first ones, were totally eye-opening. So in particular, there's a thing called style of planet called a hot Jupiter, where this is something that's like four times the mass of Jupiter, and it's closer than Mercury. So it's really just an absolute like poke in the eye to the idea of nebula theory. And there's something else going on, and there's some incomplete part of this. And the evidence that you see from all of our exoplanet discoveries, I can't think of any of the 1,000 or so. I haven't looked at them all, but of the 1,000 or so solar systems that have been discovered, they're not all analogs of Earth, let alone some appreciable fraction of them. So they all tend to do weird things. So there's a failure here, and nobody quite understands. So the part that is successful is that if you find a big cold cloud of gas, like these things called the pillars of creation in Orion's Belt, this is where you find very young stars and a lot of new star formation. If you really zoom in on one of them, so the central star is blocked out like in the coronagraph, you see a protoplanetary disk. The protoplanetary disk is about 100 AU. That's about the size of our solar system. So I think this is a T Tauri star. There's a lot of really young stars in Taurus. And they seem to have these disks formed, so great. Looks like everything's going to be on the ecliptic when they form planets. So those two things are really good. So that was a success. So believe in the protoplanetary disk. Believe in the cold cloud of gas part with some chemical enrichment, very cold. But then the other stuff we'll have to kind of revisit and take with a grain of salt. So any questions about that stuff? Yeah. Yeah. It must be, because there's a limit on the size of terrestrial planets. So there's an upper limit on which something could be terrestrial and rocky, or else it would like collapse under its own weight. So it is absolutely a Jupiter-like planet. So you cannot have something that's 900 times the mass of Earth and have it be like an Earth-like planet. So it would just collapse under its own weight and melt. So it must be some sort of gas giant. Yeah. Yeah, it's a chemical and compositional thing. So, and it's absolutely known. So when you detect exoplanets, you can find their mass. And this thing is, almost 1,000 times the mass of the sun. It's kind of crazy. Yeah, but you got to wait until we talk about exoplanets. Good. Other questions? Okay, you guys look like you're ready for a quiz.